Hello, welcome. This is part 6 in our exploration of Lagrange's theorem. Exploration of Lagrange's theorem. Lagrange, and this is part 6 of this exploration. Well, what's Lagrange's theorem? When Lagrange's theorem is talking about this idea, well, suppose we have G a finite group. G is finite. We take H a subgroup of G. We're wondering, is it really true that the order of H must divide the order of G? Is this a true statement? Is that true? That's what we've been exploring in this entire series. And it turns out that the strategy we've been using is the following. Well, in the previous video, part 5, that was part 5, so this must be part 6. In the previous video, all we did is we looked at a group G, right? And we try to okay, let's make it bigger and clearer. Why not? The bigger the better, right? Okay. Well, all right, so we have a group G, right there, group G. And what we were saying before was, well, maybe we can partition G. And the idea was we could break up G into a bunch of cosets. Okay? If the group G was considered to have the elements G1, G2, all the way up to some Gm, the idea was maybe we can break up G into a bunch of cosets. So, there's a plane outside. So, anyways, so for instance, here H is being taken to be a normal subgroup of G. So that we have maybe G1H, right? So we could break G up so that we have maybe G1H is one coset, G2H is another coset, G3H is another coset, and so on and so forth up to GMH. And we're thinking about these cosets and wondering whether they actually successfully partition G. Because we've been able to establish before that if we can get a set, any set, for example, if we're able to get this group and break it up into partitions P1, P2 up to, let's say, some Pk. If we're able to show that every group element, every Gi is in some partition, if we're also able to show that each of these partitions, each Pi is some coset, if we're also able to show that the PIs, the partitions are pairwise disjoint, if we're able to show this, which seen before that if we're able to show this, then we're basically able to prove that the order of the subgroup must divide the order of the group. But the question is, do these conditions always hold? And we realize that actually we're able to guarantee before that every element of the group is in some partition. We're able to do that. That is, if we break up G into these sorts of partitions, G1H, G2H, G3H, up to GMH, well, we can guarantee that every element of the group is contained in some coset. So condition 1 was satisfied. Just by construction, we've constructed every partition to be some coset of the form GIH. So condition 2 was satisfied. Now the issue we had before was the idea that, well, pairwise disjointness was hard to guarantee. And in fact, we saw that in general there's no reason to suppose that the Pi and these partitions that we came up with are pairwise disjoint. The conclusion this led us to considering was the idea that, okay, fine. So merely just considering all the possible cosets may cause a problem, because some of them we may not be able to get non-empty intersection. That is, it's possible that for some two of these cosets, let's say if I does not equal to j, right, if I does not equal to j, it's possible that G sub I H intersect G sub j. There's no reason to suppose that this is not possible. That the intersection of two of these cosets, where I does not equal to j, that it's not obvious to suppose that this intersection is empty. It may actually end up being non-empty. That is, this coset GIH and this coset GJH may have something in common. And so, well, if this is true, then our third condition can't be satisfied. So it looks like we're screwed, and in a sense we are, but can we work our way out of this messy situation? How could we, what can we modify this partition into a partition that will guarantee us that indeed, one, every group element will be in the new partitioning, every element, every partition will still be a coset, and that the new partition that we've created actually has pairwise disjoint partitions? Is there anything we can do to redeem ourselves in a sense? Right, so, well, our strategy for doing that was to conduct a study. Well, okay, it could be possible that the coset GIH and the coset GJH have something in common. The intersection is non-empty. But let's kind of explore. The idea was, let's explore what that means. What does it mean for GIH and GJH to have an element in common? And the idea was the following. Well, if GIH intersect GJH is non-empty, it means that, well, there exist some H1, say, and H2, right, elements of our subgroup H, such that, well, such that GIH1 equals to GJH2. That's what it would mean to have some element that's in here, in the coset GIH and in the coset GJH, right? And the idea is that every element in the coset GIH is of the form GI times some element of the subgroup H, and every element of the coset GJH is of the form GJ times some element, let's say H2 of the subgroup H. And to say that they have an element in common is to say that GIH1 equals to GJH2 for some H1 and H2. Alright, so from here already we can establish some things, because the elements of H have actually been picked. The elements of H1 was selected to be an element of the subgroup H. And if H1 is an element of the subgroup, well, subgroups are still groups, and groups always have inverses. So we can left multiply this equation, our first equation here, we can right multiply it by H1 inverse, thereby obtaining the following. We'd obtain that GIH1 times H1 inverse equals to GJH2 times H1 inverse. Now H1 times H1 inverse gives us the identity. So we end up with GI equals to GJ H2 H1 inverse. That's what we end up with. Okay, so what does this tell us? It tells us the following. Well, it tells us that the coset GIH can actually be rewritten, since GI equals to GJ H2 H inverse. The coset GIH can actually be written as GJ H2 H1 inverse H. We've just substituted GI for what it's equivalent to anyways. Okay, now if we suppose that H consists of the elements, okay, and why did we use H? Fine. If we suppose that the set H, the subgroup H consists of the elements alpha 1, alpha 2, alpha 3, all the way to some alpha r, right? Then saying that GJ, right, so hard eraser, welcome. All right, so basically saying that, oh wow, okay, so saying that GJ, oh wow, the pen's really misbehaving. So GJ H2 H1 inverse, right, multiplied by H is really equal to, well, whatever this thing is multiplied by every element of H. So we end up with, well, we now have GJ H2 H1 inverse, multiplied by, now we have a set obviously, multiplied by alpha 1. Then we have Gj H2 H1 inverse multiplied by alpha 2. Then we have Gj H2 H1 inverse multiplied by what? Alpha 3. And we continue this process until we end up with, well, Gj H2 H1. Oh, not everything is not inverse. So okay, here we made an error. What we're really saying instead is that it's H1 inverse over here. Over here it's also H1 inverse. We multiply all of this by alpha sub r. So that turns out to be our coset. Our coset Gi H2 H inverse H, which actually, by the way, is the same as GIH, turns out to be this. Okay? Well, notice, I mean, all of these elements, Gj, H2, and H1 inverse, are still elements of the group. That is, they're still elements of the group G, because H is a subgroup, and so every element that's in H is also in G. So we could simplify our calculation a bit, do this instead. So now we have, since multiplication is associative, we can rewrite our thing as, well, Gj times H2 times H1 inverse alpha 1 plus, okay, let's erase that, okay, plus Gj H2 H1 inverse alpha 2, and we continue that process all the way up till Gj H2 H1 inverse alpha r, right, the last element of H. Okay, well, notice that alpha 1 is an element of H, right? So the elements of H, we wrote them as alpha 1, alpha 2, alpha 3, up to alpha r. So whatever this is, right, it's, oh, I mean, maybe first thing to notice is that if we just consider the things that are in bracket, oh, there's no plus here. Did we do pluses? Jeez, okay. Right, these are not pluses. These are these are commas, right? Just elements of a set. Okay. Right. So we notice something here, that if we just consider the things in the brackets, they appear to be permutations of the set. That is, here, okay, so let's do that on the side so we don't end up contaminating the calculation. If you look at the things in the bracket, they kind of seem like getting H1 inverse and multiplying it by H. And that actually turns out to just be, well, because H1, that would be H1 inverse times alpha 1, H1 inverse times alpha 2, etc., up to H1 inverse times alpha r, right? That's what H1 inverse H would be, right? So see, that looks exactly the same. Here we have H1 inverse alpha 1, here we have H1 inverse alpha 1, here we have H1 inverse alpha 2, we also have H1 inverse alpha 2. So the idea is, if we look at the elements over here, these elements in our set over here, we're getting the idea that the things that we put in brackets, H1 inverse alpha 1, H1 inverse alpha 2, H1 inverse alpha r, is just some permutation of the subgroup H, right? Because remember, if the things in the, if these things that we've bracketed in these circular brackets are basically of the form H1 inverse times H, remember we proved before, H1 inverse is an element of H. So H1 inverse times H just equals to H. We proved that before, right? If we have H times H, where H is an element of H, H just equals to H. H1 inverse is also an element of H, so H1 inverse H just equals to H. What that means practically for us is that none of these elements equal to each other. So each of these, H1 inverse alpha 1, H1 inverse alpha 2, all the way up to H1 inverse alpha r, those are just permutations or a rearrangement of the group H. Okay? So basically, we may as well think of these brackets, we may as well, basically what we're saying is that what we have here is equivalent to, okay, so, alright, might have written something too far ahead. So So if each of the brackets is just the same as h1 inverse multiplied by h, that means that, convince yourself that here we now have, what we have here is just the same as multiplying gjh2 by alpha 1. We're not saying that this particular, we're not saying that this particular piece, okay, well, right, so we're not saying that this particular piece, that gjh2 h1 inverse alpha 1 equals to gjh2 alpha 1, but we're saying that gjh2 alpha 1 has to be one of the elements over here. And the reason is that because h2h inverse is a permutation of h, what that means is that for some alpha I, whatever alpha I is, for some alpha I in our setup here, for some alpha I in our setup, let's use another notation, maybe alpha s, alpha t. For some alpha t, h1 inverse alpha t is just equal to alpha 1, right? Because all we're saying is that if you multiply h1 inverse by all the elements of h, which happen to be alpha 1, alpha 2 up to alpha r, if you multiply h1 inverse by all elements of h, what we end up with is just a permutation of h, which means that there exists some alpha t, right? There exists some alpha t element of h such that h1 inverse alpha t equals to alpha 1. And this is true for all of them. So that means that each of these h inverse alpha 2 give us some element of h. So we might as well think of the entire thing as, and each of them is multiplied by the same thing, gjh2. h1 inverse alpha 1 is still multiplied by gjh2. h1 inverse alpha r is still multiplied by gjh2. So which means that, please convince yourself that we can rewrite this set that we have above here, this equality, we can rewrite it as gjh2 alpha 1 times gjh2 alpha 2 times gjh2 alpha 3 all the way up till gjh2 alpha r. Okay, so these sets are still equivalent. And now we notice something again. Well, h2 times alpha 1, we have h2 times alpha 2, h2 times alpha 3, h2 times alpha r, right? We're multiplying all of them by gj. So, alright, maybe we should have used a different color. Let's use a different color. So we notice that h2 times alpha 1, h2 times alpha 2, h2 times alpha 3, h2 times alpha r is really the same. If you consider just the things in the purple bracket, it's really the same as getting h2 and multiplying h by it. That's the left coset of h formed by h2, because that ends up giving us just h2 alpha 1, h2 alpha 2, all the way up till h2 alpha r. So what we're saying is that h2h, because h2 is an element of h, is just the same as h. It's a permutation. So again, similar reasoning to before. See if you can convince yourself that from here we can now make the following leap. Okay, oh, let's go back to our usual colors. So we can make the leap and say that the above equality gives us this equality now. This is the same as gj times some alpha 1 times gj times some alpha 2 times gj times alpha 3 all the way till gj times alpha r. Okay? Well, but this is the same as just pulling out gj from the left. We could do that. Now we have gj into alpha 1, alpha 2, alpha 3, all the way till alpha r. Right? But what is this alpha 1, alpha 2, alpha 3 up to alpha r? Well, we had set that equal to h before. Remember, h was alpha 1, alpha 2 up to alpha r. So we're really saying that this equality is now giving us the fact that gj, this set is just gj times h, because this whole thing is h, right? Okay, so what have we just established here? We've just established the following, that, well, Gj H2 H inverse H, right? So we've established that Gj H2 H1 inverse multiplied by H, the coset formed, is the same as the coset Gj H. Okay? But before we'd proved that Gi actually equals to Gj H2 H1 inverse. So this means that this coset here is the same as the coset GIH. So what are we really saying? We're saying that GIH equals to GJH. Okay? And where did we get the idea that GI equals to GJH2H inverse? Answer, we got it from here. Yeah, where did we get it from? That's actually a good question. Must be somewhere in our chart. Okay, yeah. Yeah, so here was the idea. We got the group G, we took a subgroup of the group G, we called it H, we broke it up into partitions, and we said that, well, this partitioning may not work because pairwise disjointness is not guaranteed. Which led us to the following conclusion, that if pairwise disjointness is not guaranteed, then it means that for some Gi and Gj, it's possible that GIH intersect GIH, sorry, right? So, okay, let's pick a different color. It's possible that GIH intersect GIH intersect GJH. It's possible that intersection is not empty. GIH and GJH may have some element in common. And if they do, we're kind of screwed. It means that our partition will not work. Okay? If our partition doesn't work, are we completely in trouble? We said not necessarily. Actually, we don't know yet, but at least let's study what it means for GIH intersect GJH to be non-empty. And what we realized was that if GIH intersect GJH is not empty, then it also follows that GI equals to GJH2H1 inverse. What this in particular has led us to conclude is the following, that actually the coset GIH turns out to be the same as the coset GJH. So we're saying that if I does not equal to J and the coset GIH intersect GJH is, the intersection is non-empty, then we're implying if I does not equal to J and GIH intersect GJH is not empty, then we can conclude the following. This implies that GIH actually equals to GJH. GIH and GJH are basically the same coset. Okay, so now we have some new information. Right? What's the new information? We're saying, look, okay, let's be given some finite group G. All right, we're gonna take the cosets G1H, the cosets G2H, all right, all the way up till GMH. We saw before that these cosets are not necessarily pairwise disjoint. But we know something. We know that if any two of them, for instance, if G1H and G2H were not pairwise disjoint, then if they were not pairwise disjoint, if they had some non-empty intersection, then that would mean that G1H equals to G2H. That means that of all the cosets we formed there, the coset G1H, the coset G2H, G3H, all the way to GMH, they either have no elements in common or they have all their elements in common. Okay, so given this information, can we modify our partition into a partition that will guarantee us that we have pairwise disjointness, without of course losing the other properties. Every group element is in some coset and every partition is a coset. How do we resolve this problem? How can we modify our partition to guarantee us that now we have that for every G, for all G in G, G is an element of some coset. Every partition is a coset. Every PI is a coset. And also to guarantee that PI intersect PJ is always empty if I does not equal to J. What modification can we make, given that we now know that cosets are either disjoint, completely disjoint, or they're equal to each other. There's no middle way. So either GIH intersect GJH is empty, or that's what we're finding out, or GIH equals to GJH. Right? There are no other compromises here. There's nothing in between. They either have something in common or they're equal to each other. Given this information, can we modify our partition to give us a partition that will guarantee pairwise disjointness and all the other properties that we really want to see happen? What answer do you have to this question? Well, notice that we do have a simple solution here. Well, what we do is, well, why don't we just start with G1H? We start with the coset G1H. Okay. If G1H has some, right, so, right. So here's the strategy. Here's now what our strategy looks like. Let's see, perhaps you came up with the same strategy. Let's get our group G. Okay, here's our group G. So what we're going to do is we're going to start with, pick some element of the group. Let's say G1. Pick G1 element of the group. Now G1H is a legit coset, right? Now if this G1H happens to, right, so let's write our cosets a little on the side here. So we're going to write G1H is a potential coset, G2H is a potential coset. Remember, our partitions have to be cosets, so we really don't have a choice in what the partitions are. They're going to be some coset. The question is just which coset is it, which cosets are they going to be? G4H all the way up till the last element, GMH. So we have all the possible cosets we can have. So whatever our partition is, it's going to be some combination of these. Okay. What about if we did this strategy? We said the following. We said that, look, let's start with G1H. Okay. Now, if G1H has an intersection with any of the other cosets, let's say G1H has something in common. G1H, let's say G1H intersect, I know, G4H. Let's say G1H intersect G4H, or let's say GIH, right, is non-empty. Okay, they have something in common. Then we know that GIH, then we'll know that G1H just equals to GIH. But if G1H equals to GIH, why do we need to include GIH in one of these partitions? Because if we write G1H, we've already included GIH, right? So no need to, in fact, this is not just true for G1H. This is not just true for GIH. We take the partition G1H, the coset G1H. We look for all cosets that, remember, the other cosets are either equal to G1H or they have nothing in common with G1H. So we just take G1H and we check which of the other cosets are equal to it. If any of the other cosets are equal to G1H, well, we don't include them, because including G1H is already including the other cosets. Then we go over to the next coset. We say, well, let's look for, now we pick some other element. Let's say G2H is such that G2H intersect G1H have nothing in common. right? They're completely disjoint. Because if they were not disjoint, if they had something in common, then G2H would be G1H. And then that would mean that G2H was already included when we wrote G1H. So we get some G2H that has nothing in common, that's completely disjoint from G1H. And then what do you think we're going to do next? We pick some other coset. It doesn't have to be G3, it could be anything, but let's say, just without loss of generality, suppose it's G3H. Suppose G3H is such that it has nothing in common with any of these other cosets. That is, G3H is not G2H and it's not G1H. Then it's a coset of its own, right? So now we have G3H, and we continue this process. Well, we ask ourselves, is there some other coset in this list of cosets, G1H, G2H, G3H up to GMH? Is there another coset that has nothing in, that is not equal to any of these other cosets? If we have such a coset, we just add it here. Let's call it G4H. And we continue this process. Question, will this process go on forever? Because if it goes on forever, then we kind of have a problem, because we're looking for finitely many partitions here, right? So over here we have some elements of G. Over here we have elements of G that, in the coset G1H, we have elements of G that are not in G2H. And G2H has elements of G that are not in G1H, and G3H has elements of G that are not in G2H and they're not in G1H. Right? So every partition, every new partition that we add contains elements of G that were not in the previous partitions. G4H contains elements of G that were not in G3H or G2H or G1H. So if we keep adding new elements every time of G to the partitions, and G is finite, can this process ever go on forever? Well, answer is no. What does that mean? It means that if we continue adding, we'll reach some L such that GLH is the last, such that L is the last coset, GLH is the last coset that will give us something unique. So that if we consider any other, say we picked some coset GIH, GIH will equal to one of either G12, G2H, G3H, or one of the cosets that we've considered here, G1H, G2H, G3H, up to GLH. So please convince yourself that this actually solves our problem. Because, okay, first of all, our partitions are cosets. That's clear. Partitions are cosets by definition. Do we ever leave out a group element? No. Right? Suppose we'd left out a group element. Suppose G was an element. Suppose you had G element of G, and G was not one of these cosets. Okay, G was left out. Well, all we'd have to do is to look at the coset GH. Okay, the coset GH, well, is a legit coset, right? If this GH is not one of these, right, if this GH is really not one of these, then it means the process never ended. It means that we should have continued. Or, so this is this is actually a challenge to put in words to express super clearly. Let's see. So okay, let's first describe the process and then establish that the conditions work. What we said before was, okay, we pick G1, G1H. G1H is picked as a partition. Every other partition that's equal to G1H we don't include anymore. So we look for some other partition, call it G2H, that is not equal to G1H. So we include that partition. Now, anything that, any coset that's equal to G2H or that's equal to G1H, well, we're not going to include anymore because it's already included. So we pick some other coset that is not G2H and is not G1H. We add that there, and we continue this process. And we're saying that every time we add a partition, we include new elements of G that we never included before. What this ends up telling us is that because G is finite and we keep adding new elements of G every time, the process is going to stop. Right? If the process is going to stop, then that means that every group element must be found in one of these partitions. That is, every G is an element of GIH for some GI. Right? Is in one of these cosets. Right? Okay, every G is in one of the cosets. The partitions are cosets. How about pairwise disjointness? Can any of the cosets that we formed have any element in common? Well, the answer is no, because they are specifically chosen to have nothing in common with any of the others, with the rest of them, right? So, because if let's say uh, let's say we found that, just for fun, we found maybe that G1H intersect G2H was not empty, then it would mean that, as we proved before, it would mean that G1H actually equals to G2H. But if G1H equals to G2H, well, would have never included G2H, because G1H, we said that everything that is equal to G1H we just discard, we only keep G1H. So G2H was chosen specifically to be such that it has nothing in common with G1H, etc., etc. So we see that the three conditions are indeed satisfied. Every element of the group is in some partition. The partitions, the way we've constructed them, and each of the partitions is a coset, right? And wait, we're probably missing some other property. What are we missing? Every group element is in here. Every partition is a coset. Oh yeah, and the partitions were constructed to be such that they have non-empty intersection. Yeah, yeah. So we've actually produced a partition. We've actually produced a partition that satisfies our three properties. Okay, so fine, we've produced a partition. Why does that mean that we've now proved the theorem? Okay, let's see why that is true. So we have our group G, all right? We pick a subgroup H of G, okay? All right? We've now broken up G into a bunch of partitions. One partition we call G1H, all right? So let's write it well. So let's suppose that this is now a partition that works. We've broken it up into G2H, and we've continued this process, and all these cosets have been chosen to be disjoint. We've continued this process until we reach some L, GLH. These L cosets right here partition G completely. Okay, now let's think about this. What's going to be the cardinality of G1H, right? I mean, ultimately the coset still consists of elements, plus the cardinality of G2H plus all the way until the cardinality of GIH. What's that going to equal to? Well, first thing we note is that every element of the group is in one of these partitions, and no element is in any other partition. This means that if we sum up all the elements that are in the partitions, we end up with as many elements as they are group elements. So it means that the sum of the number of elements in this partition and this partition and the partition GLH, all the partitions, is going to give us the cardinality of the group, the size of the group G. Thus, okay, but we also know something else, and we proved this before. Every coset, if we pick some element G of the group, the coset GH, so we looked at it before and we'd seen that, look, if we get any group element G, if G is an element of the group, and we consider the coset GH, the cardinality of GH is actually just equal to the cardinality of H. Right, so we had proved that before. If you've forgotten, please try to think about why this is true. So this simplifies our equation, because our equation now becomes, well, cardinality of H plus cardinality of H plus all the way up till cardinality of H. So that's what we now have, equals to the order of G. Okay, That's our current situation. All right. So question, how many cardinality of h's do we have here? Answer, as many as there were things to add in the first equation. How many things did we add in the first equation? There was G1, G2, G3, there were L elements. Thus, it means we have L cardinality of h's. So this equation can now be written as cardinality of h times L equals to cardinality of G. Okay. Well, if cardinality of h times L equals cardinality of G, what does that mean? It means that L equals to order of h, or cardinality of G over cardinality of h. Well, if there exists some positive, some natural number, some integer, if there exists some natural number L, remember L was a natural number. Okay. If there exists some natural number L for which cardinality of G divided by cardinality of h gives us that natural number, well, what does that tell us? That tells us that cardinality of h does indeed divide the cardinality of G. Right. So we've actually successfully just proved Lagrange's theorem, right? We've just proved that, look, if G is finite, right? So question is, where did the finiteness come in? We never seem to use the idea of finiteness very much. Here's where the idea of finiteness comes in, because if G is not finite, what does it mean to talk of the cardinality of G? Okay, well, you may say, well, we may say the cardinality of G is actually infinity. Fine, right? Let's grant this for the time being. Well, what about H being a subgroup of G, right? Well, whatever H is, what does it mean to divide infinity, some number, by infinity, right? Because looking at cardinality of G over cardinality of H, we kind of think about infinity over some cardinality. And that this is meaningless. At least we don't, let's not say meaningless, but let's say our current knowledge of mathematics doesn't really know how to make sense of this idea. And so that's why we restrict G to be finite. But given that G is finite, well, cardinality of G is some number, cardinality of H is some number because they're finite, their division makes sense, and we're saying if they're finite, then this always equals to some L, some natural number. So we've really just established that if G is finite, then cardinality of H divides cardinality of G. Right? This is Lagrange's theorem. Right? A really deep result that turns out to actually be very useful in calculation and in just understanding groups. So we've now finished with it, but we've spent so much time trying to understand and explore Lagrange's theorem, come up with see why Lagrange's theorem is true. So we might as well, first of all, we only know Lagrange's theorem theoretically. We only know it theoretically. We've seen it in terms of H and G, but we've not seen it in action. We've not seen examples. What are actual examples of Lagrange's theorem in work? If we know Lagrange's theorem, what does that imply? What does Lagrange's theorem enable us to do with groups? What are the consequences, right? One, we've not seen Lagrange's theorem in action, so no examples, right? And if you have no examples for something, you don't really know it. So no examples, right? So we need examples, and we need to see what are the consequences. What are the consequences of Lagrange's theorem? Another way of saying that is, what is Lagrange's theorem good for? And so we'll tackle that in the next video. Otherwise, thank you very much for watching this video, and have a relentless week. Bye.